All right, welcome back to 1 week before your operating system's final. Isn't that scary? So, Lab 6, I told Satao to start marking them ahead of time so that if you're done, you get your mark back, you know you're done, you don't have anything to worry about for the week leading up to it. So, ask away, otherwise, watch the YouTube recording. So, anything we want to particularly go over? Otherwise, we can just go over final questions. I had a request from to do our midterm virtual memory question. Any preferences to what I do? All right, so spoke up first. So here, let's quickly go over our virtual memory question. So, system page size of 64 kilobytes. Here I told you what the size of 1 kilobyte is in powers of 2, just in case you forgot. So this is, whoops, that's a big one. This is 2 to the 6. So 2 to the 6 times 2 to the 10 is 2 to the 16. So that is our page size. PTE size is 16 bytes, which is 2 to the 4. So system supports a giant physical address, so that relates to how big our page table entry size needs to be. So that's why it's 16 bytes. Here are some truncated page tables, so that just means I don't show you all the entries, just the first few, and I show you below. Then first question, how many page table entries can you fit in a single page? Well, page size divided by PTE size. So 2 to the 14 divided by 2 to the 4, that's 2 to the 12, right? 2 to the 12. 2 to the 16, sorry. 2 to the 16 divided by 2 to the 4. Too many 4s. So 2 to the 12. Good on that? All right, so if we only have a single level page table that fits on a page, what is the maximum size of bits of the virtual address we can support? Well, it would be VPN. It's always VPN and then offset. If we only have a single level of page table, well, then guess what? We just have like a whole L0 here. And the number of bits we need to for our index is essentially 2 to the what power is how many entries I can fit on a page. So that's how many things I have to index in my page table. So this would be 12 bits, and this would be 16 bits because of the page size. So if I add them together, well, then that is 28, right? All right. So then for the system with a single level page table, assume the root is at ppn A, which means, remember, the physical address always looks like this as well. So ppn offset. So in this case, well, if it starts at page ppn A, that means this is A, and it fills the entire page. So that offset can be any number because, well, the whole page table fits on that. So if we were to draw or to note the starting address of that, it would start at address 0, just like for arrays, it all starts at index 0. So in this case, we have a 16-bit offset, so that's 3 hex zeros. So it would start at address A0000. So if we try to translate this address, where this is the virtual page number and this is the offset, then, well, we don't have to translate the offset, and this is where we would look up our L0 index in this case. So we would look it up at index 1. So the page table at A000 is this one. And then what is at index 1? Well, it's this. So we would see that it is valid, so we can use it for translation. And the ppn is E, so that is our final translation. We just take the VPN, replace it with the ppn, which is E, and then keep the offset the same as 777. Good so far? All right. So same setup above, except I'm using the virtual address this. So all that changes is this, which is the L0 index. Otherwise, it's exactly the same. So if I try and translate that address, same thing, I go to the same page table and I look at index 2. Oh, guess what? Its valid bit is 0, so I can't use it to translation. I'd get a page fault, and in my program, I'd probably seg fault or something like that. So I would seg fault at that because the valid bit 0. So still good? Still with me? All right, next one. So we do this with 2 levels of page table. Same thing, each one fits on a page, maximum size of virtual address. So now we have L0, L1, and then our offset. So this is still 16 bits. This is now 12, and this is 12 as well. So we just add them all up together. So then if we do that, we get 40 bits, right? All right, so now for that page table with a 2-level page table, assume the root page table of process 100 is ppn B. So that means it starts at address B0000. So I'll just go draw it here. So this is the L1 page table for process 100 is this one. So if we translate this address, 177777, what physical address do we get? Well, if we draw that all out and fill it with all the padding, everything has leading zeros. So this 000 would be our L1 index, then 001, then 7777. L0 index, and then offset. Wow, my writing's getting bad. All right, so in this case, I look at my L1 index is 0, so I go look at its page table, look at index 0. That means the ppn is D and it is valid. So that means L1's level 0 page table starts over here. So L0 for process 100 starts here. And if I go back and look, well, the L0 index was 1. So the L0 index was 1. That corresponds to this entry. So since it is in my L0, that's the final ppn I use for that virtual address. So it is 9 and it is valid. So I would just substitute this whole VPN for the ppn, which I would get just 9 and then the offset 7777. Right. Okay, that says same system for question, yeah, all good so far? All right, then same system for question 24. Assume the root page table for process 101 is C. So it would start over here. L1 for process 101 is C. If we translate the virtual address 1, 2, and then that is the offset, what physical address do we get? So our L1 index is 1, our L0 index is 2, and our offset is 4, 7, 8, 9. So in this case, if we look at the L1 index, we get this. So at index 1, it says it's valid, and it says the ppn is at D. So it turns out that the L0 for process 101 is also here. And then it's also asks that we have to do the rest of the translation. So the L0 index now is 2. Oops. So we get to look at this one. So it is currently not valid, so we would get a page fault. If it was valid, then our final address would be 82789. But it's invalid, so we have a page fault at our L0 lookup. All right, good. Any questions about that? So now it says, given our processes with the root page tables, are there any issues? To make sure they have completely independent memory, explain why or why not. Well, there is an issue because they're both sharing an L0 page table. So if you allocated memory in one process, it'd be allocated in the other process. Like if it got a physical page for it, you could see it in the other process. They're sharing pages, and since they're sharing the page tables, all the translations will be the same. So if I tried to translate anything at address in process 100, if I tried to translate something with an L1 index, of 0, and then in process 101, if I tried to translate anything with an L1 index of, what is it, 001. Because those map to the same L1 page table, L0 page table, anything I put here any memory that has the same L0 index in both of them will map to the same page. So this, I don't know, let's just make up a number, 0, 0. That maps to the same physical page because they use the same page table, so it'll always map to the same physical page as long as their indexes are the same. So if I have this and like that, that also maps to the same physical page because it's using the same L0 page table. So, good. Any questions about that? Yep.
Why did this question support a 128-bit physical address? Was that just to trip us up or something?
So the question is, why did we say the system can support a 128-bit physical address? Because it wasn't even to trip you up, it was to justify the PTE size. The PTE size is 16 bytes, which is gigantic. So the PTE, remember what two things does a PTE have to have in it? Yeah, physical page number and permissions, and the permission should at least be a valid bit. So in that case, well, I needed, basically I wanted them all to have nice hex numbers, and I wanted to justify why the PTE size was so big, because 16 bytes is equal to 128 bits, and then my PPN would be equal to 128 minus the offset, so 128 minus 16, which is whatever. So I'd need 112 bits for my PPN size. And then I have 16 left over for permissions and stuff like that, so it's actually justified. If I said that it supports 64-bit physical addresses and 16 or an 8-bit or 8-byte 8-byte PTE size, then it'd be like, oh, okay, that's too small, that's impossible, which was a question before. All right, anything else we should do? If not, yeah? Do you have any locks and data races? All right, that's a good subject, everyone's favorite. So, good lock question. That doesn't look like a lock. That doesn't look like a lock. Oh, that looks like a lock. All right, want to do this one? Oops. Here, I will give you some time to read it, and then we can see if we want to do it or skip it. We want to do it? All right. So, code snippet, we have 3 threads, then thread 1 locks mutex 1, then 2, thread 2 locks mutex 2 and 3, and thread 3 locks mutex 3, then 1. So we only have 3 thread, 3 independent mutexes, and each thread executes a different function. So first question says, identify and explain a deadlock condition that can occur in this program. Can this deadlock? Sure.
Yeah, because each thread can execute the first line to get the lock for like index 1, index 2, index 3, and either.
Yeah. Yeah, we have a circular wait, so we could have the case that thread 1 locks M1, I'll just write it shorthand, and then we execute thread 2, it locks M2, then we execute thread 3, and it locks M3. Now, in this case, no thread can proceed further, so thread 1 cannot proceed because it's trying to acquire mutex 2, but thread 2 has mutex 2, so it can't make any progress. Thread 2 is trying to acquire mutex 3, but it can't get mutex 3 because thread 3 has it, so it can't make any progress. And then finally, thread 3, well, it's trying to get lock 1, so thread 1 has lock 1, it can't make any progress, no threads can make progress, therefore deadlock. Or if you want to give this a name, this is a circular wait. All right, good. Definitely have a deadlock, yep.
If you didn't write that it was a circular wait, would you lose marks?
No. Yeah, if you didn't write it was a circular wait, you did not lose marks as long as you explained what the deadlock was. Generally how I tell the TAs to grade is like, if they understood the concept, full points. If they didn't, well, then use their judgment. So you didn't have to say circular wait as long as I knew what you were getting at. All right, next question says, propose a solution to avoid the deadlock in this code. Modify the code and describe your proposed solution. Briefly explains how it addresses the identified deadlock. All right, how would we fix this? Yeah.
What you could do is, for the second lock, instead of just locking it like that, you could use try lock. So try lock mutex 2 and thread 1, try lock mutex 3 and thread 2, and try lock mutex 1 and thread 3. And if you're unsuccessful, you can unlock the lock you're already holding, and then you wait, and then you do one more thing that I don't remember.
So you try, you unlock,
Lock again, I think.
yeah, then you wait. So you unlock whatever you gave up, so M1, wait, and then lock M1 again, and you do that for each of them. So you eliminate the whole hold and wait thing. So if I don't get both locks, I give up the first lock I got. What's another way to fix this that I can do in one line? Well, just swapping around 2 lines. Anyone see solution 2? Yep.
For thread 3, maybe if you swapped it, mutex 1 locks first and mutex 3 locks second. And of course, switch the unlock calls as well. And then you do the same thing for thread 2. You switch which lock gets locked first.
Switch them both?
No, you only need to switch one.
Yeah. Okay, if I only switch around thread 3, then I also do not have a deadlock. Why don't I have a deadlock in that case?
Because it won't pass the first lock.
Thread 1 and thread 3 won't be fighting each other for the lock.
Yeah, well, they won't be fighting each other for a lock. I essentially eliminated the circular weight because I always acquire locks in the exact same order. So if I always acquire locks in the same order, I won't have the circular weight, right? The condition with the deadlock is like lock 3 was held and tried to acquire lock 1. So if I swap the order where I always get lock 1 first, I don't have a deadlock.
Are you talking about the order in thread 1 and thread 3? They should be consistent with thread, that order, that's what you're talking about?
No, just the order between all the mutexes. So I always acquire mutex 1 first, then always acquire mutex 2 second, and then always acquire mutex 3 third. And if one's missing, I don't have in that order. But in that case, if I just swapped around those two lines, in this one I would acquire M1, then M2. In this one I would acquire M2, then M3. And then this one I would acquire M1 and then M3. So always in the same order. So 1 has the most precedence, followed by 2, then followed by 3.
Oh, so it should be consistent on all the threads, not just...
Yeah, all the threads, yeah. It has to be consistent for all the threads. Because otherwise, if it wasn't, then you could have a circular weight between the threads.
But
Oops.
let's just assume, forget thread 3 for now, like thread 1 and thread 2, the order of M2. So we can, let's pretend we didn't have thread 3, right? And
Yeah,
instead of mutex 3, that would be mutex 1. We should swap the order
yeah,
for thread 2, okay?
yeah. All right, here's a bonus question. If I only have thread 1 and thread 2, is that a deadlock?
I'm assuming M3 is M1.
Nope, M3 is M3. No, right? I don't have a hold and wait. The only lock they share is mutex 2. The other one's not shared, so whoever gets mutex 2 can get the other one with no contention. No one else is waiting on it. So be no case for a deadlock in that case. All right, cool, bonus question.
Sorry, just to be clear.
Yeah.
If M3 was M1 in that case, that would be a deadlock, right?
If what? If M3 was M1?
Yeah.
Yes, then that would be a deadlock.
Okay. But if we swap the orders, it won't be a deadlock.
Yep. Yeah, if you swap the order, so if we just have thread 1 and thread 2, and they're both ordered like that, essentially whoever gets lock 1 is guaranteed to get lock 2. So we don't have a deadlock. But if we swap it around just like this, wow, that was really bad writing, sorry. It just, well, thread 1 could get M1, thread 2 could get M2, and now they're waiting on each other. All right, holy crap, that was, just swapping 2 lines, that was 6 points. Sweet. All right, center force, yeah? All right, so here, let me start deleting stuff, so pretend you didn't see it. Yeah, all right, you didn't see any of that. Still can't see it. Okay, I should probably use something better.
Don't you have like a blank solution of
Oh no, that's not, yeah, I should have. This one I screwed up and like, I made it in such a way that the solution, I like finished it, ran it through, printed it, and then did the solutions on it and had no good way of going back. So, yeah.
on the final exam, will there be a lot of short answers like the midterm or pretty much just long answers?
Yeah, so question, will the final exam have a lot of short answer like the midterm? No. So I think there's 5 short answers.
They're not like, 10 marks or something?
10 marks each?
No, is there one of the short answer questions like 10 marks?
No, no, the short answers, I believe, between 3 to 5, if I remember.
So
But
everything's going to be long. Each question is going to be like many questions, I guess.
yeah,
Short answer.
yeah. So there's going to be several topics. They'll say at the top of the page what it is, like exactly like this. Set of 4 is 15 points for all of it, and then it has multiple questions throughout it.
So is it like one question dependent on a previous question? Like it can cascade if you got something wrong, like part A, when you reach part F, let's say, would it carry over?
They usually don't carry over. There's one mega question that like starts over fresh. So like halfway through it just starts over, but it's the same kind of concept. And other than that, it's like same thing, tell me different things about it. Usually they try and be independent. But anything that's not, if you made a mistake before, you don't get penalized for it twice. All right, so wow, that looks terrible. All right, so you're given this code, so we have 8 threads. We got a center for that we have no idea what it's initialized to. We have a run that initializes everything, and then we have a call to initialize thread, and we have this condition. So we want all cores to execute this only after initialize everything finishes, and we only want thread 0 to execute this. So initialize thread should run only after initialize everything happens, and only one thread should call initialize everything. So we have a little bit of an ordering problem here. So it says, assume we have n threads all set up to start executing the run function. Each thread receives a unique thread ID. In addition, that initialize semaphore executes before any threads get created, so it's safe to initialize the semaphore. So then it says, using a single semaphore sem, enforce the synchronization constraints specified in the comments. You may add code directly above in C or pseudocode, and be sure to give the semaphore an initial value. Try to make a solution that supports any number of threads. Assume that thread 0 always exists. For a maximum of 7 points, you may use total threads and assume that it's the number of threads executing the run function. So for that, you could have multiple semaphores, as many as you want. So that was just another solution you could come up with, but let's see if we can come up with a solution that just uses a single semaphore. So if we want only thread 0 to execute this, well, it should probably be in an if. So if thread 0, thread ID equals 0, then, well, we should probably just let it call initialize everything. So how would we stop other threads from executing? Yep.
You can subtract the semaphore by 1. Like if its initial value is 1, you can just subtract it to 0, and then no other thread will, I guess, enter.
Yeah, so the decrement, what is the function call for it? Do we remember what it's called? To decrement. Wait, all right. Semaphores get to wait on stuff. So if we're not the main thread and we shouldn't execute that initialize thread function, well, in here we should probably just do a sem wait on whatever the semaphore. So if we want all these threads to wait and actually not execute, what does the initial value have to be? Well, first, everyone remember what a semaphore is?
1, 0. If you wait on a 0, it blocks.
Yeah, so semaphore is not just 1, 0, it's just any integer. So it's just a number, 2 operations that are atomic. I can post, which will increment it by 1, and I can wait, which will decrement it by 1. And if it's currently 0, it'll just sleep that thread until it can successfully decrement it. Think of something else, maybe. All right, so if I want these threads to actually wait, what should the initial value be? 0. All right, so if it just looks like this, well, if threads 1 through 7 start executing, well, they'll be stuck here until eventually thread 0 runs, and it runs this. So how would it free all of the other threads?
Incremented after running.
Yeah, increment it after running thread 0. So I could post, and I could just post that's sen. Whoops. Oh, I made a mess of things. All right, I will write it in this color, sem post. So now, if I only have one post, that only lets one thread run, right? What else should I do?
As well.
Huh?
Post in the else as well after the wait.
Yeah, I could post right here as well. So now if I have 8 threads, well, each one, after it decrements it, would increment it to let another thread run. So I could have as many threads as I would want to do this. Yep.
Would you also accept posting 7 times in thread 0?
Yeah, so that posting 7 times in thread 0 was this answer. So that answer capped you at -2. So if you want to, yeah. If we want to use total threads, we could just post total threads -1, or even total threads, doesn't really matter at that point, and just have a wait. So both solutions are acceptable, one's slightly more acceptable. Yeah.
Wait, so if you were to post 7 times on the semaphore, would it cause a thundering herd problem? Or that doesn't exist for semaphores?
So it wouldn't cause a thundering herd problem because 7 things can execute, so you wake up 7 things. That's what you want. With a mutex, the only reason we have a thundering herd problem is because with a mutex, we know we can only have 1 thing running. So why bother having 8 if we can only execute 1? Here, we have 7, we can execute 7. Yep.
Just to be clear, like once a thread calls sem wait, it cannot continue until some other thread has incremented the.
Yeah, if it's 0.
Okay, so the sem post on the sem wait.
Sorry?
Oh, never mind. I answered my own question. Sorry.
Yeah. Okay. Yeah.
Could you explain the sem post and the sem wait again? Because, like, aren't they supposed to block the other threads?
No, so we don't care if the other ones run in parallel, and this we can run in parallel, so we don't really care. So we want, after the initial thread initialize everything, we could have the rest of them run in parallel if we want. So this will set off the chain, so that would change that 0 to a 1, and now every thread that waits, it would successfully go ahead and decrement it from a 1 to a 0, and then, well, it would also, once it gets by the wait, it would increase it back from a 0 to a 1, and it would essentially wake them all up, which is what we want. Yeah.
Does that second post, like, it's kind of confusing to me, like, why we're calling post immediately after calling wait, like.
We just wanted to wait at the start before thread 0. After that.
Yeah, the wait is just to prevent any other thread other than thread 0 from executing. So they all get stuck on that wait, and then eventually when thread 0 is done, one of them will pass the wait, and then that will post, then cause another one to wake up, post, cause another one to wake up, post, cause another one to wake up, post. Jesus.
Yeah, side question. What's the second argument in sem init?
Sorry?
If you scroll up a bit, what's the second argument in sem init?
Oh, this one?
Yeah, I forgot.
Not relevant for us because I told you it wouldn't be, but it was like that P shared. So it's whether or not the center for is in shared memory. So if I set that to 1 and I forked, that center for would be the same in both processes. But I said I wouldn't do that because it's already confusing enough. All right.
Additional variables next. Where are we done this question?
Are we done this question? So we did that. Is there anything else? Consider the following solution without center fours. Oh, okay. So this is an example of a question that, same idea, but doesn't carry on. So if you got the first one wrong, it doesn't matter. So here is a solution without center fours. So we check if we're thread 0, then we initialize everything. Otherwise, we just yield once. So assume that we have cooperative user threads. Explain why or why not this solution is correct. Wow, that's worded terribly. So does this work if I have cooperative user threads, aka your lab 4?
For like the queue, is it gonna be like if you go to the end of the queue?
Yeah, you can assume that it's your lab 4 implementation. Yeah, so assuming you have an implementation similar to lab, well, for you guys it's lab 4. So if it's in FIFO order where you get thrown to the back, then if everything would essentially have its turn and then everyone would get skipped, no matter where thread 0 was, it would eventually run, and then it would run, initialize everything before anything else, and then they would all continue past that. So that would work. All right, next part. Assume we have cooperative kernel threads running on multiple cores. Does it work now? No, right? So even if they yield, well, if I actually had enough cores, they could all be running in parallel, so that yield might not even do anything. So depending on the scheduler, you might have thread 2 or whatever make it here before any other thread, and whether or not it yielded might not even make a difference. Because they're kernel threads, the kernel can go ahead and schedule them in parallel. You don't get to tell the kernel what to do for the most part. So that makes sense? Yep.
Yields will just continue, and then run initialized thread.
Yeah, if they're kernel threads and you have way more CPU cores, if you yield, it could just be like, okay, you're yielded, it's your turn immediately again. Go for it.
It'll just continue from that line.
Yeah, and then just continue. Yep.
I was just wondering, like, in our implementation, we use thread join to block, right? So then,
Yeah.
could that still enforce the queue? Was there a way to like completely block the user thread in lab 4?
No, so join was blocking the thread, that was it. Yeah, so in lab 4, if I had you implement more, you could have implemented thread sleep. So that could have blocked a thread until some other thread called wake up and unblocked it. You could have probably implemented that, it just would have taken some more time. Yep.
This might be a little side question, but I forgot, like, what are the applications of cooperative user threads? Like, if there's no real parallelism, why would we use them?
So even if you have a single core, like cooperative threads might be good if you want to switch, make progress on a bunch of tasks at a different time. Like you want to be able to switch, make some progress, switch to something else, make some progress, switch to something else, make some progress.
Like in the banking example.
Sorry?
Like in the banking example we did.
Sure, banking example or a web server or anything like that.
The banking example kernel threads. We use P threads.
Yeah, but we could have done it with user threads if we wanted.
Why could we have done banking example with user threads?
Why not? Anything you do with kernel threads, you can do in user threads. You just won't get any benefits. But if they're user threads and they're like doing I/O or something, well, if one thread blocks, then the whole process gets blocked, right? So that's the main drawback for that.
Wait, what do you mean by one thread gets blocked from I/O?
So if one thread like makes a read or a write system call that needs to like physically read and write a file from, for example, your file system, that's slow. So that system call is blocking, so you won't return from that system call until that operation's done. You've read something from the disk or written something to the disk. And in that case, your process is just blocked, right? It can't, it's in the middle of a system call.
One thread blocks all of them.
And then it's like, if you're in the middle of a system call and you're blocked, you can't respond to any IO during that time.
Yeah, if the kernel only knows about your one user thread that made that system call, well, it just knows that whole process is blocked. If you have user threads, the kernel doesn't know that that process has other threads that could execute. All it knows is that, hey, there's one thread I know about. It's doing a write system call. I will tell it when it's done. Okay, so we got 10 minutes left. Any other pressing things, or should we go to the next one? Condition variables. Condition variables, file systems. Wait, which one is this? Oh, this is the. Okay, my screen died. Cool. So page replacement. We shouldn't have to do over page replacement. Everyone knows page replacement, or at least knows to look at it. All right, clocks are good. So threads question. Oh, there's a bank question. Does it have deadlocks? Here's a center for question. Memory allocation, disks, virtual machines. Yeah, condition variables, I think it was just a short answer on this one. There, short answer. Briefly explain the purpose of condition variables and how they are used in conjunction with mutexes to synchronize threads in a multi-threaded program. You want to do that one? So, anyone want to tell me what the purpose of condition variables are and why you need a mutex with them? Yep.
Condition variable allows you to wait for a condition before putting in a multi-threaded program.
Yeah, so, and why do I need a mutex with it?
I can't see. I was just reading the line.
Oh, you just, God damn it. All right. Anyone that just doesn't read my lines? That was a good one. All right, so it also needs a mutex, well, because a condition variable is basically a queue, so it needs to be able to add itself safely to the queue without a data race, so that's one reason to use a mutex. The other is that, well, it needs to put this thread to sleep, it needs to give up the mutex so that another thread can go ahead and grab that mutex, hopefully update the condition variable without a data race, and then, when you wake up, you go ahead and you try and lock it again. Okay, that screen's dead. All right. So, just a short answer question, but for you, you might want to know how condition variables are used slightly better. Yeah, you know the function calls and know it's essentially a queue. I remember I did something with one. Long answer. Long answer, but like half a question long answer. That's the mega question. And by mega question, it's like 25 instead of 20. Maybe it's worth 30, I don't remember. Yep.
How many sections are there for the exam? There's like one short answer, but like how many other sections?
There's one short answer off the top of my head: processes, threads, virtual memory, file systems, semaphore/condition variables, locking. Sorry? Page replacement, yes, of course. Yeah, page replacement. I think that's it.
Memory allocation?
Nope. Oh, I shouldn't have said that. Maybe. Maybe, but no.
Basically, everything we did after the midterm, after the
Yeah, it's more heavily weighted towards after the midterm, minus important things. So processes, well, everything involves a process. As long as I show you code, that's a process. Can't get away from that. And virtual memory is always fun.
What about disks?
Disks are fun. Disks are okay. Nothing major though. This one had disks. Briefly explain the concept of RAID 5. And hey, I guess I took inspiration for this one because this one only has 5 short answers and then goes right into questions. So yours kind of looks similar to that. Yep. No. Okay. All right. Anything else for the last 5 minutes?
Can we do the file system question?
File system speed run? Yeah. Quick.
Any tips for the final?
This exam is good. Realize that I wrote it, so it won't be exactly the same as this. So anything that this doesn't quite test, you should be responsible for. So topics are the same, but obviously the questions aren't going to be the same because, well, exams that are the same year over year don't really test anything. Tests who got the last year's final. So you got a request for file systems real quick. No virtual machines, nope. All right, file systems. All right, let's speed run this. All right, for the following questions, assume your file system has a block size of 4096. Each pointer to a block is 4 bytes. Inodes are 128 bytes each. What is the minimum amount of space in bytes you need for a file system, like your lab ext4, to store 1,000 files? Assume that each file is 96 bytes in size. Include the size of the inodes in your calculation. You may skip the final calculation if you don't have a calculator. So, how much space on the drive would a single one of these files occupy? That is 96 bytes. And you can see the answer anyways. So even if a file is smaller than an I/O block, well, a regular file will still consume an I/O block no matter what. So each of them would need a single block, which is 4096, and each of them would also need an inode. So add that, you need that many bytes per file. So times it by 1,000. If you didn't have a calculator, leave it like that. You'd get that many bytes or a fair number of bytes. So next question. So for the previous question, how many bytes are lost due to internal fragmentation? You may say 0 bytes if that's the case.
Is it 4,000 times 1,000?
Yeah, 4,000 times 1,000. So for each file, well, they get an I/O block of 4096. They're only 96 bytes, so we have 4,000 bytes lost due to internal fragmentation per file. Therefore, if we have 1,000 files, then we have 4 million bytes lost due to internal fragmentation, which, is most of that number. All right, so this is a question that I thought of when I was copying a bunch of small files in Windows and it was super slow. And then I was like, oh yeah, this course. So why might copying a directory containing a single large file be faster than copying a directory with many small files, even if the total size of the small files is less than the size of the large file?
Is it because you're just switching where the inode is pointing to? Like a single switch rather than many switches?
No,
Many small files.
not quite, yeah.
Pretty sure it has something to do with the cache where it stores in the cache, but it doesn't actually copy it. And like it might show you that it's already been copied, but you need to actually flush the cache out to be fully copied.
So this is copying a file to a new thing without any caches involved or anything. So like for instance, what's 4,000? It is like 4 megabytes or something like that. So let's assume like a 4 megabyte file versus that 1,096 byte files. So, yeah.
Purely because like every file has an inode, and then you just have 1,000 inodes to work with
Yeah, well, in this case, for a single large file, there's just one single inode, and it points to blocks. Those blocks are all going to be full, except for essentially probably the last one. So it's essentially going to have 0 internal fragmentation because it's a single large file. It's only going to waste some space on the last block. And aside from that, it's just one inode. If there's a bunch of small files, it needs to copy an inode for each of those, which in this case is bigger than the file itself. And to read the contents of each of those, well, it might actually have to access more blocks than that single large file because there's so much internal fragmentation. Reading a block is what the file system's doing, and if it consumes more blocks, it's going to be slow. And in Windows, if you see, once you get to a whole bunch of small files, the performance goes like that for the copying speed. That's because the copying speed only measures the contents getting copied from the contents of the file. It doesn't include like the I/O equivalent on Windows or anything like that. So it's doing a bunch of more disk accesses, and it's not really copying anything. It has to read a bunch of blocks. All right, and we're over time. So with that, just remember, pulling for you. We're all in this together.